Hey guys, so we're gonna move into impulse and momentum, and when we talk about impulse and momentum, what we're really analyzing are collisions between objects. So we have to think about a collision. So a collision is just gonna be it's a very short interaction, um, very short interaction, and when we talk about very short interaction, we're talking usually in milliseconds, little tiny fractions of a second that the objects will be in contact. So you could think of like a tennis racket, and the ball comes in and bounces off of it. It's that time period at which the force is applied to the ball and how the velocity changes and all of that. That's what we're going to be talking about. So the idea is that an object starts with some velocity, some initial velocity, say v naught, experiences a force for some time period, very short time period, delta t, and leaves with a new velocity. Right, so you have some initial velocity, experience a force, have some new velocity. Even if it's the same magnitude, it's still opposite in direction. But we'll do two-dimensional later in the level. All right, so what actually happens during a collision? So let's watch this little piece of a video. Let me see if I still got it up. Yeah. Sorry, let me move it over. Okay, so what we're gonna be looking at right here is this is a facility. I think it's the University of Massachusetts. They test baseballs and baseball bats, and so they've set up a high-speed camera here, and they're going to record the collision between a baseball and a baseball bat.
You ready?
And what we want to pay attention to is what's happening during the collision. So you saw how fast that was, but if you notice, you actually get a deformation of the ball. Look at this; it almost looks like it's filled with water. And so you can see there is some time period, so we get some deformation, and this happens with any type of collision. So it's like we'll talk about energy later on, and so you can see that it's almost like a spring energy that's being stored. But anyway, we'll talk about that. Let's watch it again, just because it's weird. Look at that thing; it's crazy. All right, so let's get back to our. So the force that the object experiences is called an impulsive force. Impulsive force. And this force that it experiences it's much larger compared to any other forces. So it's a very large force in comparison, very large relatively. So if we're looking at a collision with a baseball bat, we don't care about gravity or any other forces acting on it, because this force that the bat's exerting is going to be much higher than anything else. So that's all that we care about. And so if we were thinking about a force graph during the interaction, so we could have some force over time. And then what's happening is there's no force being applied, and then the objects come into contact, and the graph kind of does this thing and reaches a peak, and then it comes back on the other side. That's what you see with the deformation. So there's some maximum force up here that's being applied, and then you can see like this is the point at which the contact begins, and then it ends over here when they're no longer touching. So it goes from some time, we'll say t naught, to some final time, tf. And so we can see that force is going to be, the impulsive force is a function of time. So our impulsive force is a function of time. All right, so what can we do with this? Well, why don't we try using Newton's second law? So we know that the force is going to be equal to the mass times the acceleration. And then the acceleration is the derivative of the velocity with respect to time. And now we can rearrange this. So I'm going to put it over on the other side. So the force with respect to time times dt is equal to m dv. And then the thing is that we don't want these d's. So to get rid of derivatives, we can integrate. And so we're going to integrate from some time to initial time to a final time for this side. And then over here, this is velocity. Well, the object comes in with the v naught. We could put that down here. You could have like v naught, and it leaves with some other velocity. So we'll integrate over this interval on the other side. So integrating over here, you get the integral from t naught to t final is the impulsive force with respect to time. And over on the other side, you'll get the integral from v naught to v final of mass times dv. And I know your integration isn't there yet. I know y'all are just learning it, but on this side, we just leave it alone. There's really nothing that I'm going to do. So we have from t naught to tf to the final time of the force with respect to time is equal to, now here I want to go ahead and pull out the integral. So since it's in terms of v and there's no v, we'll add a v in. So this becomes mv. And we're going to evaluate that. We're going to find the difference from v naught to v final. So we get that from time 0 to, the initial time to the final time of the force with respect to time is going to be mvf minus mv naught. And it's this quantity right here that we want to talk about. So this is my impulse. My impulse is going to be, we can actually use another letter for this. This is going to be equal to j. And this is a vector. So that's an impulse force. All right, so let's look at all this stuff. So this right here, this is just the symbol for impulse. And this says that the impulse is going to be the area under the curve of a force versus time graph. It's a little t, force versus time. And then over here, so this introduces a new quantity called momentum. So we have momentum. And for momentum, we use a little p. And momentum is defined as the mass times velocity. So what we're looking at here is actually the change in momentum. So we could say that this is equal to the change in momentum. So the impulse is defined as the change in momentum. So impulse is the change in momentum. And this is the impulse momentum, the momentum principle. This definition here, actually this way with the delta p, this is on the equation sheet. I think I have it up. Let's see. Yeah, right there. So your impulse is the area under the curve is the change in momentum. And now we're going to talk a little bit about this one. So it says that force is the change in momentum over time. So that's Newton's second law. So let me get a new page open. So Newton's second law. Newton's second law, the acceleration is equal to the net force over mass. And if we rearrange that, we can get that the force is the mass times acceleration. However, this mass needs to stay the same. We really can't use this if we have a changing mass. And where does that happen? So if I had a rocket flying up into the air, right? As it's expending fuel, as its fuel is decreasing, its mass is decreasing. So we would need to account for that. So anyway, Newton originally didn't talk about it this way with acceleration. What he talked about was momentum, because mass times acceleration is the derivative of velocity with respect to time. And then I can move that inside, so I get that it's the derivative of mv. Sorry, I drew that too long, with respect to time. And that is just simply the change in momentum with respect to time. So this is Newton's second in terms of momentum. Yeah, so this is really useful, particularly when masses start changing. So we talked about the momentum principle. How about graphs? So let's look at graphs real quick. So suppose I had a force over time graph and we'll do momentum over time. All right. So an object comes in, experiences, let's say this here. So an object is going to come in, collide with a wall, and then bounce off and back in that direction. I'm going to draw it at an angle, but it actually comes straight back. Okay, so that's what's happening. So during this right here, we have an impulse. We have a force that's applied over time. And since it's to the left, we define positive to be right. Since it's to the left, then that force is negative. So what we end up getting is that we get this kind of dip like this. Yeah? All right, so now the momentum. So originally the ball had some positive momentum, and then what happened is it experienced a force which decreased it and gave it negative momentum. And these things would line up. Oh, that's a terrible line. Yeah. So up here, this area under the curve, this is the impulse. And this has been added to find the new momentum. So this amount right here is right here under the curve. And in this case, since it's below the line, then this is a negative area. So it's been decreasing. It decreases the momentum. All right, so this is just to give you a feel for it. You're going to be doing a bunch of calculations. Again, it's just going to rely on the definition of momentum. So just to recall, momentum is mass times velocity. Change in momentum would be, which is your impulse, is going to be your final velocity minus your initial. And that's equal to your force over force times time. Okay, have fun.